Hello, everyone. It's a great honor for me to give this Bright Spark lecture. Thanks to Professor Budima and the organizing committee for today's workshop. This is the topic I will talk about today. Before my presentation, I would like to acknowledge our research team for their contributions. I will start with these figures showing rutting, which is a primary distress mode of unbound granular pavements. Rutting basically is deformation through shear and densification due to traffic loads. As you can see here, rutting can come from both underlying unbound granular layer and subgrade soil. Given that we have sustainable issues due to increased traffic loads challenging our pavements, it's time to ask, can we develop a more resilient pavement? Currently, the unbound pavement design is most empirical and uses elastic analysis. So can we take advantages of the up-to-date developments in unsaturated soil mechanics to further advance the pavement technology? I will try answering this question through today's presentation. Here I will show an overview of our approach. It's through a computational framework to simulate the processes involved in testing, construction, and operation of the pavements. They integrate and optimize these processes as needed for intelligent pavement construction. For instance, if we model cyclic loading involved in the processes of construction and operation on the vehicle loading, then we can get a better estimation of stress that's experienced by the soil and better design the laboratory test. Vice versa, if we do a better laboratory test, which better replicates the pavement response, eventually we can get a better estimation of rutting. The key tool in this integration is the computational framework, which should allow capturing the essential features during these processes. In our computational framework, the constitutive model can accurately simulate the hydromechanic shakedown of soils at saturated and unsaturated states under a great number of loading cycles, which we believe is very important to model variable cyclic loading involved in the process that I mentioned before. Because of the time limitation, I will only present the key aspects of our constitutive model in the following slides. If you are interested, you can take a screenshot and refer to the papers listed here for a full story. The constitutive model is based on the sandstand framework, which captures the fundamental role of stress ratio in controlling granular soil behavior. Stress ratio here is defined as the diabatoric stress divided by mean effective stress P dash. These two figures shows the schematic representation of the model components. Left-hand side is a triaxial stress plane, and the right-hand side is a stress ratio pi plane. We have dilatancy surface, critical state surface, reference surface. With this surface, we could capture many features of granular soils, including softling, dilatancy, critical state behavior. Recently, some researchers found that it's very difficult to accurately predict the plastic stress accumulations as the number of loading cycles increases. So to overcome this, following Corti et al. In 2016, we use a memory surface that changes in size with plastic strands to describe the variations in soil stiffness during cyclic loading. In our model, we address many challenges associated with a great number of loading cycles and take stress history into account. For instance, multi-stage cyclic loading with various loading amplitudes. To get an idea of how the model works, I will show an example by simulating a drained triaxial cyclic loading test performed on a saturated soil. And the unsaturated soil example I will present it later. So first, let's look at what are these four figures here. So this one is the deviatoric stress versus mean effective stress. And this one shows the deviatoric stress versus axial stress. Here, this is the plastic modulus component H. You can consider it's an indicator of soil stiffness. And this versus number of loading cycles. Then this one shows the axial plastic strength versus number of loading cycles. As cyclic loading proceeds, the memory surface expands in response to volume compression to capture the soil stiffness increasing. So at the same time, you can see H increase. And that's why you see a reduction in axial strain here and a reduction in axial plastic strain here. Eventually, the soil sample exhibits a shakedown state with marginal plastic strain accumulation. Now, with this computational framework, let's see how we do the integrated simulation. First, look at this pavement response under traffic loads. If we take a soil sample beneath the pavement surface like this, when the weir is right on top of it, it's subjected to axial stress, and along with that, it will expand in radial direction, right? Because of the resistance coming from the surrounding pavement materials, radial stress will build up as residual stress. So in this scenario, axial stress is greater than radial stress. But when the weir goes away, things may go other way around, and soil undergoes extension. And this feature cannot be simulated by traditional IRT test. Then someone may ask, what kind of laboratory test can capture this feature and better replicate pavement response? In SparkUp, we are proposing a radial constant stiffness test as a better simulator of pavement performance, capturing into a single element. It's done by this PUMA device. It provides a constant stiffness Ki here by a rubber band. So this rubber band is used to represent the resistance coming from the pavement. When the soil is loaded just like a triaxial vertically with horizontal loading, what happens is the axial deformation will take place to simulate the rutting. And along with that, laterally, the soil will expand. When soil expands, the rubber band will increase the resistance by increasing the radial stress. And the radial stress will be locked in. If we reduce the axial stress, then the radial stress can be greater than the axial stress. So soil undergoes extension. This PUMA device also has other advantages. For the details, you can refer to this paper. We did many simulations of this constant radial stiffness test at different initial soil states and stress levels. Overall, a good agreement between the simulation and the test results was achieved. Here, I just show one example of unsaturated soil. It's under constant water content conditions, and the applied load pattern is shown over here. These two figures present the results of axial net stress versus axial strain. And these two are deviatoric stress versus mean net stress. As you can see, the deviatoric stress goes to negative, which means extension. The top one shows the evolution of axial plastic strain. Now let's check animation to see how the model works for the example of unsaturated soil. This figure shows the effective stress path, and this one will demonstrate the stress strain path. Here we'll show the evolution of degree of saturation and suction. So suction is back calculated through the water retention behavior. And this diagram will present the axial plastic strain against the radial plastic strain. During cyclic loading, the effects of degree of saturation and suction changes on the cyclic hardening are mainly through their effects on the memory surface evolution. You can see the degree of saturation is approaching the measured one at the end of the test. And this diagram has a very interesting feature, which I will demonstrate in the next slide. Here, the same diagram, I plotted our simulations with different KR values. Here is the KR value equal to 150 MPa, which is close to the stiffness of the tested sample. See here, it falls into this contraction zone, and the sample gets hardening and very limited radial plastic strain takes place. So it's like a one-dimensional scenario. When decreasing the KR value, for example, to 0 here, which means ILT, confining pressure doesn't change. So you see this guy. There is a small part falling into this dilation zone. That means the sample has dilated during cyclic loading, which means weakening. So this scenario may not happen in the field. Now the question is, what the KR value replicates the loading conditions in the road construction and operation? To answer it, we need to simulate these boundary value problems, right? Currently, we are implementing our constitutive model into a finite element package so that we can better estimate the KR values to be used in the PUMA test. In conclusion, I want to say, like, all these processes are connected to each other and should be treated as a unity. By utilizing all this information in design, then we can build more resilient pavements. Hope through the presentation I answered this question, which I placed at the beginning. Thank you, everyone. I'm Liuxin. I'm very happy to answer any questions.